Hello everyone. In this video we'll discuss about module 4 arithmetic. This module is dedicated to a discussion of computer arithmetic. It introduces the fundamental issues related to the arithmetic operations like addition, subtraction, multiplication, division and circuits used to support these computations in computer. This module considers the way programs are executed in a computer from the machine instruction set viewpoints. These are the outlines or the topics from the module 4. So, so in this module, we starts with an introduction to number systems. In that we'll discuss arithmetic operations and character, addition and subtraction of sign numbers. We introduce a number of algorithms together with the hardware schemes that are used in performing integer addition, subtraction, multiplication and division. And we see like how to design a fast adders for the addition operation. Then in the multiplication we'll discuss about some Booth's algorithm, different algorithms we use how to perform a multiplication of a positive numbers, then signed operand multiplication, and we have a fast multiplication and integer division. So before going to the topic, we'll discuss how to convert decimal to binary and binary to decimal format. So as you know, in the decimal to binary conversion, we need to divide the decimal number repeatedly by decimal number 2 to make it, so decimal number it is of base 10. So we have to convert that into a base 2 number, that is nothing but a binary number. So here I have taken decimal number as 35. So keep on dividing this with the decimal number 2. So I will divide 35 by 2. So we will get 17. So 17 2s are 34 and the carry 1, remainder 1. Then you will divide the 17 by 2. So that is the 8 2s are 16 and remainder is 1. Then 2 4s are 8, remainder is 0. Then 2 2s are 4, remainder 0. Then 2 1s are 2, remainder 0. Then you have to take these numbers along with the quotient 1. So your binary value, it becomes 1 0 0 0 1 1. So in this format you have to take, you know how to represent a binary number. So you have to take it in a 2 to the power 0 format. So here you have to take these values and you have to write it in from MSB to LSB position. So this becomes MSB. So from MSB to LSB direction you have to write. So this becomes your binary number, that is 1 0 0 0 1 1. So we'll just verify the decimal value for this. So wherever it one value is there, bit value 1 is there, binary value 1 is there. So just consider that number with the base 2. So 1 into 2 to the power 0, that is nothing but 1. Then 2 to the power 1 into 1. So 2 to the power 1 is nothing but 2. Then here 0, just ignore these values. Wherever 1, so next one is in 2 to the power 5. So 2 to the power 5 is nothing but 32. So 32 plus 2, that is 34. 34 plus 1, that is 35. So that is nothing but like how to convert a decimal to binary format. So now we'll see binary to decimal conversion. So here the given number is 1010 with base 2. So now we have to convert this into a base 10 value, that is decimal value. So the place value for this we'll write in this format. So that is 1010. So from the LSB we'll write it as 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3. So now while converting, wherever the value 1, we have to consider those place values. So the 0 value we need to ignore. So 0 into anything is 0. So here 0 into 2 to the power 0 is 0. 1 into 2 to the power 1, that is 2. 0 into 2 to the power 2, that becomes 0. Next is 1, that is 2 to the power 3. So 1 into 2 to the power 3, that becomes 8. So in the decimal format it becomes 8 plus 2, that is nothing but the 10. So the equivalent value for this binary is nothing but 10. Decimal value 10. So this is another example. So we are converting decimal number 17 into binary value. So we'll keep on dividing this 17 by 2. So you will get this binary number. Okay, so again we want to convert that back to decimal value. So just take the place values and multiply with this and add all the values. So you will get a decimal value 17. So this is the binary representation for the decimal value 70. So next we will discuss about signed integer. So here there are three major representations: sign and magnitude, 1's complement, 2's complement. So to explain this representation, we assume that here we'll assume that the machine word is of 4-bit data, and it is of 16 different values can be represented. Roughly half are positive and half are negative. So now one by one we will discuss about these number representation, and here in all the three formats MSB value is 0 means it is a positive number, and if it is the MSB value is 1, that means it is a negative number. So this concept is same for all the three formats. If MSB value is 0, it is a positive number. If MSB is 1, that is a negative number. So we'll discuss one by one. So first we'll discuss about sign and magnitude system. So sign and magnitude is a very simple representation of negative numbers. In sign magnitude, the first bit is dedicated to represent the sign, and hence it is called a sign bit. And the remaining bit represent magnitude of number. So that's why the name sign and magnitude system. So how to obtain a negative value? So negative value is obtained by changing the MSB from 0 to 1 of the corresponding positive value. Okay, so we need to when we want to represent a negative value, first we need to consider the positive value of that, and in that positive value, the MSB value, we have to change it to 1. So that becomes the negative value in sign and magnitude system. So for example, we'll take plus 5 here. So plus 5 is represented by 0, 1, 0, 1. Okay, so that is the binary value of the decimal value 5. So here MSB value is nothing but 0. That means it is a positive 5. Okay, so how to convert this into negative 5? So what we have to do, we have to keep all this, the three bits, so these bits, and this is the MSB. So here it is 0, so we need to change it to 1. So that becomes minus 5. So here this in sign and magnitude, this MSB bit is called a sign bit, and the remaining these three bits are called magnitude bits or magnitude. So that is the name sign and magnitude system. So in if the sign bit is 1, it represent 1 represent negative number, and if the sign bit is 0, represent positive number. So in sign and magnitude representation of a n-bit number, the first bit will represent the sign and rest n minus 1 bits represent magnitude of a number. So next we will discuss the ones complement representation. So here negative values are obtained by complementing each bit of the corresponding positive number. Okay, so we'll take here, we want to convert, obtain a negative value of 3. So what we have to do, first we need to consider positive 3. So that is 0, 0, 1, 1. So it is nothing but 2 to the power 0 and 2 to the power 1. So 2 to the power 1 is 2 plus 1, that becomes 3. So this is here binary number for the decimal value 3. So now for ones complement to get a minus 3, so what we have to do? We have to convert each bit into the, we have to complement each bit here. So here it is 1, so we have to take it as a 0. Complement of 1 is 0. Then again 1, 0. So here we have 0. So complement of that is nothing but 1. So the minus 3 we can represent by using 1, 1, 0, 0. So that is a ones complement. To get a negative value, we need to complement each bit of the corresponding positive number. So in the 2's complement system, forming the 2's complement of a number is done by subtracting that number from 2n, or in other words we can define this as the 2's complement of a number is adding 1 to the 1's complement of that number. So how we will get 2's complement? So to represent a negative number in this form, first we need to take the 1's complement of the number represented in simple positive binary form and then add 1 to it. So that becomes the 2's complement, the binary number in 2's complement form. So in the number representation, if the single bit addition means when we add 0 and 0, the result is 0. When we add 0 plus 1, 1. 1 plus 0 is 0. When we add two ones, so 1 plus 1, that becomes 0 and 1. So here it represents 2. So 2 to the power 0 is 0. 2 to the power 1 is, so here it is 1. So 2 to the power 1. So it represents decimal value 2. 1 0 represent decimal value 2. So here when I add these 1 plus 1 0 and 1 becomes carry. So that is nothing but a carry out which will go to the next stage. So that I will write it here. Okay, so that is a carry out. So in the multiple bit addition, for example 6 plus 3. Okay, these are in a decimal format. So 6 we need to convert into binary, that becomes 0 1 1 0. Then plus 3 0 0 1 1. When we add these two, so 0 plus 1 1, 1 plus 1 0, 1 carry. So again 1 plus 1 plus 0 0 and 1 carry, so 1. So this nothing but 9. You will get this as a 9. Okay. So here if you see here the carry which is coming from the previous stage, okay, so that we will call it as a input. Okay, that is carry in. The carry which is going to the next step, okay, the which is forwarded from the previous step to the next step, so that is nothing but output carry or carry out. So this is a carry in which is coming as an input from the previous stage, and the carry which is going out to the next stage, that is called carry out. So now in detail we'll discuss sign and magnitude representation. So this is just a magnitude representation of a number, 4-bit number. So here there are 16 different values can be formed by using 4-bit value. So as I said, in sign and magnitude, high order bit is if it is 0, it is a positive number. Then if it is 1, means it is a negative number. So 3 low order bits is the magnitude here. So the high order bit will represent the sign, and the low order bits represent magnitude, and the number range for n bits, it is from plus or minus 2 to the power n minus 1 to minus 1. So, and one important thing here is there are two representation for 0. So for plus 0 and minus 0, there are two representation here. So sign and magnitude, if I take a plus 4, this is the value 0 1 0 0. If I want to convert this into a minus 4, then just I have to change this MSB into 1. So that becomes minus 4. So here, so these are the positive numbers we have taken. So plus 0, plus 1, plus 2, plus 3, up to plus 7. Okay, so next what we are doing here, so we are converting, because when the MSB value, we are taking only 4-bit value, and that MSB should be 0 for positive number. So up to plus 7 we can represent by using 4-bit value. Okay, so next what we will do, we will take the, we'll represent in a negative value. So we'll start from 0. Okay, so we'll start from 0. So this is a sign and magnitude representation. So next we will see the ones complement representation. So in ones complement, first we have to take a positive number of the for the that given number, and then we have to add 1 to means we have to complement each bit in the given number. So plus 4 is given, that is 0 1 0 0. We need to complement each bit in this binary number. So 0 will become 1, 0 becomes 1 here, then 1 becomes 0, 0 becomes 1. So that becomes minus 4. So like that, here we have 0 to plus 7. So what we will do, we'll just make the complement of this plus 7, that becomes minus 7. So we are just complementing each bit, so that will give you the negative value. So all these are negative values for the this positive number. Subtraction implemented by addition and ones complement, still two representation of 0. So here also there are two representations for 0 value. This causes some problems and some complexity in additions. Next is a 2's complement representation. So here 2's complement, we have to take to represent a negative value, we need to consider positive value of that number and take 1's complement of that number and add 1 to the LSB of that 1's complement. That will give you the 2's complement of the given number. So here we will take from 0 to plus 7. Then what we will do, we'll just take the 1's complement and we'll add 1 to it. So these becomes the negative value for that number. So these are the numbers for the means negative value for the positive number. So only one representation for 0. So in 2's complement we can see only one representation for 0 and one more negative number than positive number. So here we have how many positive number? 3, 6, 7, 8. So here we have 3, 6, 7, 8. So here minus 8 is that is one more number than the positive number. So here plus 8 is not there. So but we got a minus 8 here. Okay, so one more negative number than the positive number. So like 1's complement except shifted one position clockwise. Okay. So this is a binary means a signed integer representation. Same value we have represented in a tabular column, tabular form. So here this is the bit number B0, B1, B2, B3. So this is the MSB and this is the LSB. So these are the three formats representation: sign and magnitude, 1's complement and 2's complement. We have taken all this binary values, 16 different values, and what we will do is we'll just take the values in positive and negative numbers. So up to 7 all positive numbers are same. So only in the negative value representation, all these number values will change. So here in the sign and magnitude, only when the MSB value is 1, that becomes a negative value. So here this becomes minus 0. Again, if it is 1 means that is minus 1. So like that we have represented in a sign and magnitude. And 1's complement means, so here the 1's complement. So 0, 1, 1, 1. When I take the plus 7, the 1's complement of plus 7, so that becomes minus 7. So this is a minus 7. So like that we have taken all the negative values. So here the same number, when I take negative means 1's complement and adding 1 to it, so that will give you the value minus 8. Okay, so these all are the negative values in the 2's complement form. So 1's complement. So how to represent a number in a 1's complement? So here we have taken the decimal value 5, and we have represented this in a 8-bit number system. Okay, so this is in a 8-bit format. We are taking 8-bit value. Okay, so then what we will do, because when 5 value we represent with a 4-digit one, right, 4-digit value. So here the MSB value is 0. So we'll extend that sign bit into another 4 value. So that becomes 8-bit number. Okay, so now we'll take the complement of each bit. Okay, we'll make a complement of each bit. So that becomes the 1's complement of the decimal value 5. So in 2's complement of a number is obtained by adding 1 to the 1's complement of that number. So first example, we'll take positive 5. So what we have to do is we have to take the 1's complement of this, and here also we are representing this in a 8-bit format. Okay, so now we'll take the complement of each digit in this number. Okay, so then we'll add 1 to the LSB of the 1's complement value. So that will give you the 2's complement format, that is nothing but minus 5 for the negative value. Again, in the second example, we have minus 13. Okay, the given number is minus 13. So to represent this in a 2's complement, we have to take the plus 13. Okay, so how to get plus 13? So you have to take minus 13 means you have to take the 2's complement form. So you have to take plus 13, take the complement of that and add plus 1. That becomes here this value. Okay, 1 1 1 0 0 1 1. So here what they have done, they have given is we have to take 2's complement of minus 13. So again you have to do a 2's complement. So change this into 1's complement. So this will be the value and plus 1. So this is nothing but you will get a plus 13. So negative value when you so here you are performing 2's complement 2 times. So when you do the 2's complement 2 times, you will get the positive value for the given negative value. So this is how to do 2's complement addition. 2's complement representation for the given number. Next we will discuss addition and subtraction, so using 2's complement method. So the two rules for addition and subtraction of n-bit signed number using 2's complement representation system. So these two rules should be followed for the addition and subtraction. So to add two numbers, add their n bits and ignore the carryout signal from the MSB position. The sum will be algebraically correct value as long as the answer is in the range minus 2 to the power n minus 1 through plus 2 to the power n minus 1 minus 1. So that means if we want to perform an addition operation, we have to add n bit number and ignore the extra carry out which is coming after the MSB position. So then we need to ignore those carry out bit. Okay, and the sum value should be within this range. The results whatever we are getting after the addition, that the result should be within this range. So if it is out of this range, then we call it as that condition as a arithmetic overflow. That we will be discussing in detail in coming slides. So the second rule is to subtract two numbers x and y. That means that is to perform x minus y. Take the 2's complement of y, because y becomes negative value here. So whenever negative value comes in the 2's complement form, you have to first take the positive of this y and take 1's complement and add 1 to it. So that means 2's complement of y and then add it to x as in rule 1. Okay, so minus y we have to represent in 2's complement form. Then whatever results you will get, that you have to add it to the value x, just like what it is there in the rule 1. And again results will be algebraically correct if it lies in the range. So here also we need to check whether the result is within this range or not. If it is within the range, there is no overflow. If it is out of this range, then overflow occurs. So we'll see a few examples on addition and subtraction. So this is the first example we are taking. We are performing for addition on two values, decimal value, that is 4 plus 3. So first we need to represent this in a binary format. So 4 is represented by using 0 1 0 0 plus 3, that is 0 0 1 1. So add these two. So 0 plus 1 1, 0 plus 1 1, 1 plus 0 1, 0 plus 0 0. So that is nothing but 7. So decimal value is 7. So here also we got 7. So next is minus 4 plus minus 3. So that is nothing but generally in the addition, decimal addition, we will get minus 7. So but here both the values are in negative, both are negative values. So what we have to do here is we have to take 2's complement of minus 4 and 2's complement of minus 3. Then we have to do a addition operation. So here we will get one extra bit. So this becomes your MSB, because we are taking 4-bit value. So 4-bit for the 2 operands. So your results should be in a 4-bit value. So one extra bit we got, that is nothing but your carry out. So we need to ignore this bit. So same here, we'll perform 4 plus minus 3. So for minus 3, you have to represent in a 2's complement form. Then you have to do a addition. So you will get 1 bit extra, that is a extra carry. So like that you have to perform the addition operation, addition and subtraction operation in 2's complement form. So simpler addition scheme makes 2's complement the most common choice for integer number systems within the digital system. If carry in to the high order bit is equal to carry out, then ignore the carry. If carry in differs from carry out, then overflow occurs. So how to calculate, how to do a 2's complement subtraction. So 2's complement subtraction is the binary addition of the minuend to the 2's complement of the subtrahend. Means adding a negative number is the same as subtracting a positive 1. So for example 7 minus 12, that means minus 5. So here what we have to do, 7 is nothing but positive number, take positive number as it is. Okay, so here we are taking in the 8-bit format. Then here it is minus 12. So minus 12, what we have to do, we have to take it in the 2's complement form of plus 12. Okay, so we need to take plus 12, take 1's complement, add 1 to it. that becomes 2's complement, so that is nothing but minus 12. Then add to the first operand, that is plus 7, you will get this answer. Okay, so that is a 2's complement subtraction. So these are the few examples from the textbook. So try to solve this. So here both the values are positive number, that is plus 2 and plus 3. Okay, so directly you can perform the addition operation, but here it is plus 4 and minus 6. So this is a negative number, so what we have to do, we have to take the positive number, that is plus 6, that is nothing but 0 1 1 0. Okay, so take the ones complement of this, so that becomes 1 0 0 1, that is a ones complement of this. Then add 1 to it, so 1 plus 1 0, 1 carry, so 1 plus 0 1 0 1. So this becomes your 2's complement of 2's complement form for minus 6. Okay, so that represents your minus 6. Then add to plus 4, whatever you get, that is nothing but a minus 2. So this becomes minus 2 in 2's complement form. So some more example we'll discuss in this. So here the example, the perform 2's complement arithmetic for 30 minus 50 using 6-bit number system and 8-bit number system. Okay, so 30 you have to represent by using 6-bit. So 30 you can represent actually by using 5-bit number, but you have to make it as a plus 30, right? So you have to add 0 here. Okay, so totally it becomes 6-bit number. Okay, so here plus 30, then it is a minus 50. So what you have to do, take consider the so take the positive 50, then take 1's complement of that, then add 1 to it. Okay, so you will get 2's complement value, that is 0 0 1 1 0 1. Okay, so then add that into a plus 30, so you will get 0 0 1 1 1 0. So like this you have to perform your 2's complement arithmetic operation. Okay, so this is the results for this. So this is how to calculate 2's complement for minus 50, and you have to add that into this 30. So here is the calculation, 0 1 1 1 0, that is 30, and this is a representation of minus 30. Okay, so next you have to take the same value and you have to represent in 8-bit number system. So same here, you have to add 2 more zeros because your MSB value is 0 and you are extending the sign bit. So whatever value is there, that many number of bits you have to add to make it 8-bit. Okay, so this is 30, and again you have to take it in a 2's complement form. So this is your value. Okay, 1's complement of this, add 1 to it, that becomes your 2's complement, add this to plus 30. So this is your answer for the 30 minus 50 in a 2's complement form. So 2 more examples on this. Take the 2's complement of the negative number and use regular binary addition. So given number is 9 minus 5. So 9 as it is, because it is a positive number, then minus 5, what you have to do, you have to take minus 5 plus 5. Okay, take plus 5, take the 1's complement of this and add 1 to it, so that becomes your 2's complement. Take these 2's complement and add to the positive number plus 9, so you will get this. So here you have got 1 extra bit. Okay, so here it is 1 extra bit, so you have to ignore this extra carry. Then again another example, here we'll consider minus 9 and plus 5. So minus 9, so what you have to do here, So you just take the positive number, means positive 9, take 1's complement and add 1 to it, you will get this value. Okay, so then that you will add it with the plus 5, so you will get this. And here also you got one extra carry, you need to ignore this. Okay, so ignore this, and if you want to cross verify, again take this value, perform 2's complement, you will get the positive value, that is nothing but plus 4. So that means this is the whatever the 2's complement method what we are using here, it is correct. Okay, so that's all for today's session. Thank you.